Hello friends, in this video we are gonna learn about bitwise operators in Python. So in Python, bitwise operators are used to perform bitwise calculation on integers. The integers are first converted into binary and then operations are performed bit by bit, hence the name bitwise operator. Then the result that we obtain after performing the operation is converted to decimal format. Now, while working with bitwise operators, you have to keep in mind that bitwise operators work only on integers. You cannot apply a bitwise operator on a float. So these are the bitwise operators: bitwise complement, bitwise AND OR XOR, bitwise right shift and bitwise left shift. So what does a bitwise complement operator do? It is also called the bitwise NOT operator sometimes. So what does this operator do? It flips every bit of the binary representation of x. So when we apply this bitwise complement operator on a operand x, it first converts the operand x to binary form and then flips every bit of that binary representation. That is, if the bit is 1, it is changed to 0, and if the bit is 0, it is changed to 1. Similarly, the bitwise AND operator performs bit by bit AND operation between the two operands x and y. So the two operands are first converted to their respective binary form and then a bit by bit AND operation is performed between each bit of those two binary numbers, and then the result which is obtained in binary is returned in the decimal format. Similarly, the bitwise OR operator performs a bit by bit OR operation. Bitwise XOR performs bit by bit XOR operation. Bitwise right shift operator, what it does, it actually shifts the bits of the number to the right and fills 0 on the voids left as a result. If the description seems a bit cryptic to you, don't worry at all. We will look at examples of all these operators one by one. So without wasting any time, let's get started on the bitwise operator. Let's flip to Jupyter Notebook. So the first operator is bitwise complement or bitwise NOT operator. So as discussed in the slide, the bitwise complement operator flips each and every bit of the binary representation. So we will discuss this in detail how it actually happens, but before that let me tell you the one-liner formula of the bitwise operator with which you can easily find the result when you apply the bitwise complement operator on a particular decimal number. So if you are applying the bitwise complement operator on the decimal number n, your result will be minus of n plus 1. So both n and n plus 1 are in decimal form. So let's verify this formula. So let's say we have a variable called x and we assign the decimal value 13 to the variable x. Now, if we apply the bitwise complement operator on the variable x like this, so this symbol is called tilde. You will find this symbol right below the escape key in your keyboard. So let's print the bitwise complement operator applied on the variable x. Let's comment out these things and let's run the cell. So as I just mentioned, if the input is n, so if here n is 13 or x is 13, so the output will be minus n plus 1 or minus x plus 1, whatever you want to say it. So the output here should have been minus 13 plus 1, that is minus 14, and that's what we have got as the output. So this was the one-liner formula to find out the bitwise result of the bitwise complement operator. Now we will discuss how it is actually working behind the scenes. To understand this, you need to have a knowledge of number conversion between binary and decimal number systems. If you are not aware of this, I have given a link in the description section of this video from which you can study this concept. So before going deep into the discussion, let me first discuss two very important concepts related to binary decimal interconversion. So these are the two things. So first, to convert a negative decimal number to binary, these are the steps you have to follow. So to convert a negative decimal number to binary, what you have to do? You have to ignore the sign, that is, you have to take the positive of the number and then convert it to binary, and then find the two's complement of that binary representation. So suppose if the number is minus 13, then you have to first find the binary representation of 13 and then find the two's complement of that binary representation, and that will give you the binary representation of minus 13. The second concept is that to convert a binary number to a negative decimal number, we have to first find the two's complement of the binary number, then we have to convert it to decimal and then add a negative sign in front of that converted decimal number. So we will look at both of these concepts when we will look at more examples of the bitwise complement operator. So here the number that is given as input is 13, right? So what is the binary representation of 13? Let's open a new notepad and let's see that. The binary representation of 13 is 0000 1101, right? So what does the bitwise complement operator do? It flips each and every bit of a binary, right? So the zeros will be changed to 1 and the ones will be changed to 0. So if we apply the bitwise operator on this binary, it will become 11110010, right? So this is the binary representation of our output, but we have already mentioned that the Python will not show you the output in binary form. Rather, it will convert this binary to decimal. Now there is one more thing. Before converting this binary to decimal, you have to understand whether it is a negative number or a positive number. To understand that, there are two ways. One way is to check the most significant bit. Now, which is the most significant bit in this binary? The most significant bit is the leftmost bit. So for an 8-bit representation, it is the 8th bit from the right and the first bit from the left. And for a 16-bit representation, it is the 16th bit from the right and the first bit from the left. So in this binary, which is the most significant bit? So this is the most significant bit, right? Now if the most significant bit is 1, then the number is a negative number, and if the most significant bit is 0, then the number is a positive number. So in our case, this number is a negative number, right? So there is another way to check the same, to check whether the number is a negative number or a positive number, and that is by checking our earlier formula. So what we said, if the input is n, the output will be minus n plus 1. So the sign of the output will be exactly opposite of that of the input. So in our case, the input is 13, right, which is a positive number. So our output will obviously be a negative number. So in these two ways, you can understand that this output or this number is a negative number. So we have to convert this binary to a negative decimal number. Now, what was the rule of converting the binary to a negative decimal number? You have to find the 2's complement of the binary. Then you have to convert it to a decimal and then add a negative sign in front of it. So how do we find 2's complement? 2's complement is nothing but 1's complement plus 1. So first we have to find the 1's complement of this binary, and to find the 1's complement we again have to simply change the bits of the binary or flip the bits of the binary like this: 0 0 0 0 1 1 0 1. Now we have found the 1's complement of this number. Now we will add 1 to this 1's complement, right? So we'll add 1 to the 1's complement, and it will become, so this will be the 2's complement of this number. This number is the 2's complement of this number. So what we have to do, we have to simply convert this 2's complement to decimal, and the decimal form of this 2's complement will be 14, right? Now what was the third step? The third step was to simply add a negative sign in front of it. So the final output is minus 14. So if we revisit the entire thing, we'll see that there were 3 main steps. Let's divide it in 3 different parts. Okay. So in the first step, what we did, we converted the decimal input 13 to binary. So this part is about conversion of decimal input to binary. The second part is about applying the bitwise complement operator on the above binary, and the third part is, this is the entire third part, and in this part what we did, we converted back the binary output to decimal output. So these are the 3 steps. In the first step, we converted the decimal input to binary input. Then we applied the bitwise operator on the binary input to get the binary output, and then we converted the binary output to decimal output. So that's how it works. So in this example, we applied the bitwise complement operator on a positive input. Now in our next example, we'll apply the same operator on a negative input. Now let's take a negative decimal number. Let the number be minus 20. Okay. So this is our input. So what is the first step that we have to perform? We have to first convert the negative decimal number to its binary representation. And what are the steps to be performed for that? Let's check that once again. So these are the steps to convert a negative decimal number to binary. The first step is to take the positive of the number and convert it to binary, and the second step is to find its 2's complement. So first we have to take the positive of the number. So instead of minus 20, we have to take 20 and we'll have to convert 20 to its binary form. Now what is the binary form of 20? The binary form is 0 0 0 1 0 1 0 0, right? So this is the binary representation of 20. Now what is the next step? The next step is to find the 2's complement of this binary. So let's do that. So what is the 2's complement of this binary? It's 1's complement plus 1, right? So what is the 1's complement of this binary? The 1's complement is 1 1 1 0 1 0 1 1. So we have got the 1's complement just by flipping the bits of the above binary. Now we have to add 1 to this binary to get the 2's complement like before, right? We have to add 1 to it, and when we add 1 to it, this is the binary number that we get. So our first step is completed. That is, we have converted the negative decimal number to its binary representation. Now what is the next step? The next step is to apply the bitwise complement operator on this binary input. So we have completed our first step. So let's draw a line here. And from here we start our next step. So when we apply the bitwise complement operator on this binary number, what happens? The bits get flipped, right? So it becomes 0 0 0 1 0 0 1 1. So this is our binary output. Now we have to convert this binary output to decimal. Now from this binary output, what do you think? Whether this will be a positive decimal or a negative decimal? So as I mentioned previously also, you have to check the most significant bit, that is the leftmost bit for that. Here the leftmost bit is 0. So when the leftmost bit or the most significant bit is 0, it indicates that it is a positive number. As it is a positive number, so we will not perform the step A and step C. So for conversion from binary to positive decimal number, only step B is required. So if we convert this to decimal form, we will get 19. So let's verify our output from Jupyter Notebook as well. Let's apply the bitwise complement operator on -20. Let's run the cell, and as expected we get 19. So this is how the bitwise complement operator works. So the next thing that we are going to discuss is the bitwise AND operator. Before giving an example of bitwise AND operator, let me show you the truth table of the same. So this is the truth table of bitwise AND. So if one bit is 0 and the other bit is also 0, then the output will be 0. If one bit is 0 and the other bit is 1, then also it will be 0. If the one bit is 1 and the other bit is 0, then also it will be 0. And if both the bits are 1, then only the output will be 1. So in case of bitwise AND, the output will be 1 only when both the bits are 1. If any of the bits is 0, then the output will always be 0. So let's look at a practical example of bitwise AND operation. So let's say we have a variable x, the value of which is 8, and another variable y, the value of which is 10. So if we apply the bitwise AND operator on these two variables, so what it will first do, the bitwise AND operator will first convert this to decimal numbers into their binary forms. So let's do that. What is the 8-bit representation, 8-bit binary representation of the decimal number 8? It is 0 0 0 0 1 0 0 0. And what is the binary representation of 10? 0 0 0 0 1 0 1 0. So now if we perform the bitwise AND operation on these two binaries, for the rightmost bit, both bits are 0, right? So if both bits are 0, what should be the output? According to the truth table, if both bits are 0, then the output should also be 0. So the rightmost bit of the output will be 0. Now we go switch to the second bit. For the second bit, we have a 0 and a 1. So if either of the bits is 0, then what we have said, the output will also be 0. So we again write 0 here. Then we go to the third bit, and for here also we have two zeros. So we'll again have 0 as output according to the truth table. Now we have both 1. So in the truth table, what did we say? If both the bits are 1, then only the output bit will be 1. So this is the output bit, and for rest of the bits we have all zeros. So the rest of the output bits will also be 0. So this will be the binary output of the bitwise AND operation. Now if we convert it to decimal, it will become 8 only, right? So let's run the cell and we get 8 as expected. The next operator is Bitwise OR operator, and we'll take the same values for the example of Bitwise OR operator as well. So let's again switch back to the notepad. So these were the two input binaries. Now for Bitwise OR operator, the output binary will obviously change. Let's see what will be the output binary. So this is the truth table. This is the truth table of Bitwise OR. So we can see that the rightmost bits are 0 and 0. So what we have said, that output bit will be 0 only when both the bits are 0. So for the rightmost bit, the output bit will be 0 as both the bits are in both the input bits are 0. Then we have got 1 and 0. So the output bit will be 1. Then we have got both 0. So we'll again write 0. Then we have both 1. So it will be 1. And then for rest of the bits we have both zeros. So it will again all be 0. So in this case, now if we convert this output binary to decimal, we will get 10. So the output of the bitwise OR operator when applied on these two variables x and y should give us 10. So let's see if that happens or not. We write bitwise OR and run the cell, and as expected we get 10. Next we shall apply bitwise OR operator on these two operands. So it will be like 8 XOR 10. Now let's again go back to the notepad. Let's erase the previous output. Okay, for XOR operation, let's look at the truth table of XOR. For XOR, if the bits are 0 and 0, the output bit is 0. For 0 1 it is 1, for 1 0 it is 1, and for 1 1 it is 0. So when both the bits are same, the output will be 0. That is when either both the bits are 0 or both the bits are 1, then the output will be 0. And when one bit is 0 and another bit is 1, the output will be 1. So if the bits are same, the output will be 0. If the bits are different, the output will be 1. So if we apply the XOR operator on these two inputs, so for the rightmost bit, we have the same bits, so the output will be 0. So for the second bit, we have different bits, so the output bit will be 1. Again, we have same bits, that is 0 0, so the output will again be 0. For the fourth bit, we again have same bits, so the output will again be 0. And for the all the rest of the bits, for each of them the output bit will be 0. So this is the binary output of the bitwise XOR operator when applied on 8 and 10. Now if we convert this binary to decimal, we get 2. So the output of the bitwise XOR operation should be 2. So let's check that, and we get 2 as expected. So the next thing that we are going to discuss is the bitwise right shift operator. As its name implies, the bitwise right shift operator shifts every bit of a number to the right. Now, how many places are the bits shifted? That depends on the value of the second operand. If the second operand is 2, then the bits are shifted 2 places to the right. If the value of the second operand is 3, then the bits are shifted 3 places to the right, and so on. So let's look at an example of bitwise right shift operator. So let's take a number 12 and apply the bitwise right shift operator, and let the value of the second operand be 2. As the value of the second operand is 2, so every bit of the first operand is going to shift 2 places to the right. So let's see how this shifting actually happens. So this is the binary representation of the first operand, that is 12. So this is the binary form of 12. Now what we have just said, we have said that the every bit of this binary will shift 2 places to the right. So this bit will shift here, this bit will shift here. So let's write them down. This bit is gonna shift here, this bit is gonna shift here, this bit gonna shift here, then this gonna shift here, and so on. Now you may ask me, what is gonna happen with the 2 rightmost bits of the original binary? These 2 rightmost bits are gonna be discarded, as there are no more places left at the right. And what will be happened with these 2 void spaces that have been created due to this shifting process? These 2 void spaces will be filled by 0. Fine. So the 2 rightmost bits of the original binary are gonna be discarded, and the voids created at the left are going to be filled by 0. So this is our output binary. Now if we convert this output binary to decimal, what will be the value? The value will be 3. Now if you look at it carefully, what was our input? Our input was 12. So the first operand was 12, and our output is gonna be 3. So what happened? 12 actually has been divided by 4. Now where does this 4 come from? This 4 is 2 to the power 2. So applying a right shift, bitwise right shift operator on a number actually means you are dividing that particular number, or you are dividing the first operand by a particular power of 2. So here, as the second operand is 2, that's why the number has actually been divided by 2 to the power 2. Had the second operand be 3, this number would actually have been divided by 2 to the power 3. So it happens like that. When you are applying the bitwise right shift operator, you are dividing the first operand by a certain power of 2. So let's run the cell and we get 3 as expected. So this output actually matches the output that we derived by this shifting process. Similarly, if we apply the right shift operator on -12, and we again keep the value of the right hand side operand as 2. So if we run the cell, we will get -3. The next operator that we are going to discuss is the bitwise left shift operator. Similar to the bitwise right shift operator, the left shift operator shifts the bits to the left, and how many places the bits will shift again depends on the value of the second operand. So let's again take this value 12, or let's copy it and paste it here, and instead of right shift, now we will use left shift. So applying the right shift operator, as we just mentioned, is equivalent to dividing a number by some power of 2. Similarly, applying the left shift operator is equivalent to multiplying the first operand by some power of 2. So let's run the cell, and as expected we get 48. Why do we get 48? Because here 12 is getting multiplied by 2 to the power 2. Now if we change it to 3, then 12 will get multiplied by 2 cube, or 2 to the power 3, and if we run the cell, we will get 12 into 8, that is 96. Now we will again switch back to MS Word and we will perform the shift operation on the binary representation of 12 to match our derived output with the actual output. So this is the binary representation of 12. Now we are applying the left shift operator on this binary, and we are trying to shift the bits 3 places to the left. So this bit will be shifted here, this bit will be shifted here, this bit to be shifted here, and so on. So the rightmost bit, that is this bit, will be shifted to this place. Now similar to the previous case, the leftmost 3 bits will be discarded and the void spaces remaining at the right will be filled by zeros. So this will be our output binary, and if we convert this output binary to decimal, we will get 96, which matches the actual output. So the actual output was 96, which has matched the output that we have derived by the shifting operation. So friends, that's it for this video. I have given you some exercise problems. Please try to solve these problems and let me know the answers in the comment section. And if you are stuck with any of these problems, please let me know and I will come up with the solution of those problems. And if you have liked my video, please subscribe to my channel so that you remain notified when I will upload more Python and data science related videos. And please don't forget to like and share my video so that it reaches a larger audience and they also get benefited from it. Thanks a lot for watching.